right, I think we're ready. We're going to work on our printer some today, but we're actually going to work in SolidWorks for a little bit first. We're going to start there, and what we're talking about in SolidWorks is called Topology Optimization. So it's a process, not specific to SolidWorks, just that's where I'm going to show you what we're doing. And the idea is that you can use processes like additive manufacturing. It doesn't have to be 3D printing, but it could be other processes too, to optimize a part. So the topology, the shape of a part, you could optimize that using software. So an example would be, I have one, let's see, where did I put that one? Here. So here's a example I found, Luxon Engineering, where they are working. Let me show you the original part. So they're working on, these race cars, and they have a design that does work. This very blocky design right here in the center that's kind of holding everything together, and they want to use topology optimization in order to lightweight this part, so make it perform the same function strength-wise, but it will be a lighter weight version of it. So there's a fly that keeps messing with me. So performance goals, you can see lightweight. They still want high stiffness. They want a one-piece design, so they don't want to have to bolt little individual components together to be able to create this design. That's one of the things that 3D printing can do, specifically more like the metal 3D printing in this case. The 3D printing that we're doing with the FDM, the plastic extrusion, you can still use this process for that kind of printing with plastic extrusion. It doesn't quite make quite as much sense because you can still create the part and just make it hollow inside, so have a lighter weight infill, more walls, that kind of stuff. So you can lightweight things a different way with FDM printing than you can with some of the metal 3D printing, although you can sort of make metal parts hollow. You just have to be careful not to trap the particles. We haven't really talked about not medical, it could be in a medical situation, metal 3D printing yet though. So here's where they kind of got their idea on, here's what the setting looks like already. So the yellow part here is their existing mount, and here's sort of the process they went through to get to the revised optimized version. So you can kind of see the yellow is the design space. So not all there's two kind of branches of this process. One is called generative design, and one is called topology optimization. They're basically doing the same thing, but in a little bit different way. The generative design, you specify material can't go here, material has to go here, here are the loads and constraints, and then it will sort of generate material between those constraints and boundary conditions that you give it. And topology optimization says, is more like what they're doing here, where the big block of material, this is where we can put stuff. And then you can see these blue areas, those are saying that we have to have material in these spots. Maybe that's a mounting surface or a bearing surface, but there's some reason that has to be there. And then the optimization part will go and eat away at all of the yellow until it gets down to the minimum amount of yellow material to maintain the design goals. So lightweight, maintain stiffness and strength and that sort of thing, while also adhering to any constraints you gave it about we have to have material in these spots. So that's sort of the idea of how this works. Now what's actually happening is a simulation. So you can notice maybe on your screen, depending on how big your screen you're looking at, is the yellow original part here. It looks like it's got all these dots on it. Those are vertices of a mesh. So this is a mesh, a finite element mesh of the part that you want. And so what's happening is the stresses in the part based on your boundary conditions, loads, constraints, all that kind of stuff, material properties. They're being calculated, and then anywhere where there's really low stress, that's being removed, and then they recalculate. So it's an iterative process of gradually eating away at the block material, the bulk yellow material here, until you're left with just the necessary stuff. So that's kind of the first end result. And then they went and did a CAD interpretation. So based on what the process, the topology optimization process said, like, we need something like this, somebody went in and like, okay, well, that's great and all. Let's make it a little more realistic. So for instance, notice in the optimized part straight out of the solver, this top right connecting boss is just kind of hanging out there, and the designer said that it doesn't look right to me. Maybe we didn't account for all the loads that are on here, so maybe when they designed this thing to simulate it, they forgot a load, or they didn't get a load applied just right. Whatever the reason, this top right piece up here is just kind of hanging out on its own, and they're like, no, we're going to connect that back to the main piece. So you can kind of see when they interpreted what the solver gave it, they're like, no, we got to have something there. And so you can see some differences. This green piece here is based on the output of the topology optimization. An engineer went in and built a similar model, but they used a little bit more sense, I guess, like design sense. Then this one that's got multicolors on it here, this is a finite element analysis. It didn't say what process, well, TET10, but I don't know what software they use to do this finite element analysis. And you can kind of see what the colors here are showing you are the stresses. So there's kind of a high stress right in this corner, right in this fillet here, it looks like, but we don't have a sense of how high is that stress. Usually in these things, the red is something that is giving you a factor of safety lower than 1, but you could actually make it give any range of numbers. So maybe they have a little concern right there. And the red one here, the final design, is what they ended up with based on the output of the topology optimization, the CAD interpretation, somebody going in and building a model that looks kind of like that, but with some sense, human sense added to it. A analysis of the green part, that you can kind of see this dotted arrow there. They had to iterate a couple of times there, possibly. And then the red part is the final design, suitable for whatever manufacturing process. Whether or not it's 3D printing, it could be, this particular piece might be a CNC milled part from a couple of different directions, or who knows. It depends on what equipment they have available to make this part. Here's just another example with a different part. So same process, but a different part. I think it's the other side. You can kind of see here are their final finite element analysis simulations of the parts that were chosen. There's the actual final manufactured parts. I can't tell if these parts are 3D printed or not. The pictures are too small. I wonder if it says here. Maybe if I read all of their stuff, it might say. They're saying that saves a lot of money just on the engineering time, not just on the fact that there's less material. These are better optimized parts than what they started with, but on the time to actually create these parts, they saved a good bit of money. And then there's the car that they go on. All right, and then if you want to go more, there's who this was created by. All right, we're going to do this process, not the whole process. We're going to do the first step. Well, the first two steps. We're going to create a block of design space, like this blocky yellow model, and then we're going to run the topology optimization. We will do one step that they may or may not have done in here, kind of in this curved arrow, where we will export that as a smooth model and look at that, but we're not going to go through the whole process here. So we're going to do the first steps. The rest of them are pretty standard. Once you've got the optimized geometry, then the rest of it is more like traditional engineering. But we're going to do those steps. Not for this piece. We're going to do a connecting rod. So these are already, this is GrabCAD. These are just to show you kind of what we're after. These are connecting rods that would connect a piston. So this one right here has a piston on top of it. The darker gray part is the connecting rod, and this red one over here is a connecting rod, but it's enclosed on this end, but it's just not showing the piston here. So we're going to design us a blocky version of one of these, put some kind of realistic loads on it, and then we're going to run the topology optimization process while it's running, because it's not instant. It does take some amount of time for this to process, and the more complicated the geometry, the more difficult things you're asking it to do, the longer it'll take. I anticipate our process, we're not going to be super realistic. I anticipate ours taking maybe 10 minutes. So during that 10 minutes while it's just sitting there processing, we'll look at our printer again. All right, so first step is we've got to go in and model. We could just go grab one of these. These kind of look like they've been relatively optimized already. You can kind of see, you know, it's thinned out in the center of the rod here. You've got fillets and everything. So we're just gonna build one from scratch, basically, as if we were creating our own connecting rod for a particular application. So that's what we're gonna do. So I've already got SolidWorks running, this is, what version is this? Let me see. I think, well, about. This is the 2021 version, so it's not the newest one. There are some newer ones. This particular process probably has not changed a lot. Maybe the background solver, you know, the actual algorithms might have changed. I don't know. This is an education edition, but it does have the licenses for the simulation on it. All right. So first thing is you got to make a part. New. Gonna make a new part. Okay. Now sometimes when I'm streaming in SolidWorks at the same time, it kind of is a little sluggish, and it may have some redraw issues, but we'll see how it goes. If you're not streaming and everything at the same time, your SolidWorks will probably run a little better than what mine's going to. But let's see. First step is let's make more or less just a blank profile that we can eat away at in our model. So I'm going to use some dimensions that are more or less realistic. I don't know what that happened. I hit a key on the keyboard, so not sure what happened there. All right, so we're going to draw on the front plane, and I think first I'll just draw a line. See, this is what I'm talking about with the redraw issues sometimes being a problem here. All right, so I'm going to make this a vertical line because with all of that going on, it's hard to tell. And it's going to be a construction line. So this is kind of our center line of our part, just to have a place to make sure the big end and small end are lined up. So we're going to say that the big end is a circle, and it has dimensions of, let's see, I wrote them down, 2.1 inches. Okay. The small end, oh, I'm on dimension. Hold on. Small end, let's draw a circle up there. Let's give it dimension of 0.9 inches. Okay. And then from the center to center, so the rod length here, we're going to give 5.7 inches. So this is roughly the dimensions if I were creating something for a V8 Chevy 350, somewhere in that range engine. These are not specific to any particular thing, but this is about what you would expect. All right. So let me go. It keeps redraw. It's going to continually give a little bit of redraw issues, but that's okay. See, it just decides to go away sometimes. All right, so those are going to be holes where we have to maintain those holes because they are going to either be up here, the small end is going to have a pin through it connecting the piston, and the big end down here is going to be around the crankshaft. So those dimensions have to be maintained. So these are going to be preserved regions, is what I will call them. I think that's what SolidWorks calls them too. All right, now we'll need some geometry around this to eat away at. So let's just make something here with I don't know. Let's say that I probably should have looked up how thick these typically are, but if my inner hole is 0.9, then let's say that this part is, I don't know, 1.3 inches maybe. That's probably overdoing it a little bit, but that'll be close-ish, close enough. All right, now let's do a similar thing down here. Now this one is going around the crankshaft. Let's say that we used a 2.1 inch inner bore. Let's say the outer part should be, let's keep a 0.3 on either side, so 2.7. Something's not right. Oh, I didn't dimension it, I guess. I just wrote numbers in to nothing. There we go. All right, so that's at least realistic, we'll say. All right, now we need to connect these together with the actual rod part. And I'll just use some lines. So I'll start one line here, and another line I'll put on the circle here and make those tangent. So I'll select this guy and the circle, make those tangent. Okay. And then I'll do a similar thing on the other side. We could have mirrored this. That would have worked. We are going to mirror it in the simulation, but just to save some processing power. Because if you have any symmetry, like half bilateral symmetry or quarter symmetry or anything, any kind of symmetry, then that will speed up any of these simulations that you have to do. Because basically the simulations are based on the number of elements, you know, the finite elements, and there might be thousands of finite elements in there, and if I can half that number by having bilateral symmetry, then I should speed up my processing time because it doesn't have to process as many elements. Plus, I don't want it to kind of create a situation where, in this case, half of the model looks one way and the other half of it is different. I want this one to end up symmetric because of the application. You don't always want that, you know, it depends on the application, but in this case I would want that. All right, let's see. I'm trying to decide if I want to go ahead and give it a head start on making the inner part a thinner area or not. I kind of think I do. So let's close this sketch for now, and then let's extrude those guys. Okay, and let's extrude them. These things, I did write that down. I think 0.94 is what they normally are. Yeah. And we'll make them center line, mid-plane, I guess is what it's called in here, so that it's half of 0.94 inches on either side. So you can kind of see it's starting to take shape there. That looks reasonable. So we'll do that. Now we do need to connect those together. So I wonder if I should maybe draw. I don't know if I can go back and use this sketch or not. I'm not sure that I can. Let's just see if I do an extruded base. Oh yeah, I can. All right, good. Now let's select those. Again, let's do mid-plane, and then not the same thickness. Let's automatically say that we know it's going to be thinner. We don't know how much thinner, but it's going to be thinner. And let's say that this needs to be, I don't know, let's do 0.5. Oh, but had some weird units in my deal there. Okay. And looks reasonable. Okay. So there's kind of our really generic connecting rod. Now, one thing about this bottom, the big end, and those are what you normally call them, the big end and the small end. Maybe not very technical terms, but that's what you'd call these. Is that this end is actually a two-part piece because it has to bolt around the crankshaft. So we need to chop off this bottom part if we want it to be more realistic to a connecting rod. So why don't we do that? We could do that with an extruded cut, but we need a plane that goes through here. And let's do a reference geometry plane. And let's look at our top plane. Oh wow, the top. Did I draw that one? I don't know that I drew that one exactly through that part or not. I don't remember how I think I don't remember. I'd have to go back to the sketch to see if that one's through the center. It doesn't quite look like it is, but maybe it is. So in that case, I don't really need that. Let's do a curves split line on, we want to, oh, I never remember. I think I want to split, oh no, these are the planes. All right, so not that. I want to split on the top plane, and I want to split this body. Actually, I want to split all of it. Split that guy too. We could do that. So now we got a split line there, and we could either, could we just delete these? Because I'm not actually designing anything. I don't know if it'll break anything if I delete these or not. Let's see. Oh no, it just deleted the split line. Don't want to do that. Why don't we just do an extruded cut, and we will extrude on that plane, top plane, and we will look down on it, and we'll draw a rectangle like that there, and zoom out, and we'll just chop all that off. Not the best way to do that, but it worked for what we wanted it to do. Now there are some other things going on here, like actually we need to be able to bolt that other half of the main cap, end cap, on here, so we need some bosses for that. I'm not sure, well, maybe, let's see what time it is. Yeah, let's go ahead and let's put those on there because it's not that hard. So extruded boss on this surface. I'm not sure why it's not automatically going to there, but let's put a midline. Actually, let's just draw some circles on the midpoint, and let's make them 1/4 inch, and then we will make an outer circle, and we'll make that one 1/2 inch. And then we'll do the same thing on the other side. So we're not actually doing a SolidWorks lesson. We're just kind of going in, and you can kind of see an idea of how this stuff works. And we're about to do the topology optimization part. All right, that looks fine. That's fine. And then let's extrude these, not that direction. Extrude them that way, and let's make them 0.75. Sound good? Good enough? And then we need to actually have holes in there, right? Because we have only half of a hole right now. So let's go back over to our sketch, grab, oh, will it not let me get, that's annoying. I can't get just that piece. It wants to get the whole surface there. All right, so we will extruded cut on that plane, and we'll line this guy back up, and this guy. And we'll extrude them, yeah, right there. Well, let's extrude a little further just in case there's some weirdness. All right, so we could spend some amount of time working on getting this thing just right. All right, but let's assume that we don't want to. Actually, you know, this little cutout right here, that part might give us some problems later on. So let's actually edit this guy so that we do extrude up to up to surface, that surface. So might still have some issues. We're not going to be too worried about it. Now would be a good time to save. So we will file, save as, and let's put this in a connecting rod. All right, so now we have it as a solid part. All right, and it's not horrible by itself. It does need a material, so let's get a material. I'm just going to use cast steel. So why not? I just didn't want to go through the material selector. Sometimes takes a while to load up, so this will be good enough for what we want to do. But it does need a material in order to actually do any kind of simulation. All right, so now you would go to your add-ins wherever. Like I've got a tab here for add-ins. You would need SolidWorks Simulation Premium to do this, because the SolidWorks Premium will do just basically static stress. You know, it doesn't do the topology optimization. It really just does static stress analysis. But the Simulation Premium does a lot of different things. So when I go to the tab over here for simulation, I can do a new study, and I've got all these things I could do. But there's topology study. That's the one I want. It's already selected. Okay, and then it looks like, if you've ever done a finite element analysis, it looks a whole lot like that. These are, you know, this menu is exactly the same, except you've got these two new things: goals and constraints, and manufacturing controls. So we've already added a material, so that's fine. Fixtures, let's do some fixed geometry. Let's say that this end is fixed and that is fixed. So those are, actually no, this end is not fixed. Let's just say that this end, let's go ahead and add that surface. Let's just say that those are fixed. Okay, then let's add our force that in the pin here. So the piston sits on top of this thing and will push down on it when the ignition happens in your combustion chamber, and then the inertia of the piston will pull it. It'll be in tension a little bit. So there's some forces. We're not going to be too serious on how this gets loaded, but here's how we're going to load it. We're just going to put a force on that surface, but we can't put it like that direction. We're going to select direction, and we're going to select our front plane probably. Yeah. And we'll use English units. And here, the way these work are, you've got a plane, and it is my reference plane because I did selected direction. And you've got to pick, was it normal to that, shearing it, you know, what way is it going? So we're going to say it's going this way, except I want this to simulate like compression, where we just had ignition and the piston is being forced downwards, which pushes compression in our connecting rod. So we will reverse the direction. So now it's going down, and way more than that. We're going to say that, I don't know, this is a 4-inch piston, and you can get maybe at the peak, combining all the axial forces here, there might be 10,000 pounds of force in this direction. We are just guessing that, but that's what we're going to say. That's our peak compressive force here. Okay, goals and constraints. Do I want to minimize the mass? Do I want to create the best stiffness to weight ratio, which is normally, it's the default one? Or do I want to minimize displacement? So sort of just stiffness, but I'm not worried about the ratio of stiffness to weight. I'm going to do stiffness to weight. Okay, and then I do have options here on what do I want to add. So I'm looking here. The current mass is 690 kilograms, so well, 690 grams. I'd like this thing to be 350-ish grams. So I want to reduce the mass by what, 50? Yeah, 50% or so. So this will aim for a 350 gram connecting rod. So, okay, that seems good. I have other options here. You know, if I need to avoid some natural frequencies, I can do that. Or if I need to maintain a particular factor of safety against some stress, I could do that. There's also a displacement constraint. I'm just going to do this one thing. It's probably already going to take a while for it to run, so I don't want to have a bunch of things that just trying to do at once. Okay, manufacturing controls. So I do have some preserved regions. So I have to maintain that guy. I have to maintain that. I need to maintain these bolt holes. I need to maintain this surface. And it's probably getting hard to see with all the little arrows on there, right? And that surface. I probably need to maintain this surface and that surface and there and there. So all of those are things that I'm thinking don't eat away at those surfaces. I could also say that I don't want it to eat away on the top of this, you know, that whole guy up there. Right? So those are my preserved reasons. I also can say that, hey, I do want this thing to be bilaterally symmetrical. So I can specify symmetry planes. And the way I built it, I could use the right plane. Right? I could use the right plane, and that way it'll only have to model and analyze half of this thing. So that looks good. And I think that's all I really need to do. There are other things. There's a thickness control, so if I have to have a certain minimum thickness or maximum at some place, then I could do that. That might make sense with the web here in the middle. Demold direction, that's good if I'm injection molding parts, or even if I'm CNC from one side, then this will maintain that I want to keep that. I want to keep that as I don't want it overhangs or anything in that direction. I just realized I could also have symmetry down this line too, couldn't I? So let's go ahead and add another symmetry control on I think that's the front plane. Actually, let's do quarter symmetry, and let's just do both of them at the same time, and then we'll erase the other one. All right, so let's, it combined them together. Okay, so good. It's smart enough to know that I only wanted that to happen once. All right, let's run this study. So now I'm actually doing a quarter symmetry model, and we will run it, and we'll let it run for a little bit so you can kind of see what's happening, and then we'll go look at our printer for a while it does its thing. I don't know, I ran a similar one earlier, and it didn't take very long, but now I've got more processing happening, so it might take a while. So what it's doing now, you can kind of see iteration 1. So it's basically, it's meshed this thing, and it is doing the finite element model and calculating the initial stresses based on our constraints and our 10,000 pound load that we applied to it. And then it's going to, based on those results, eat away some material and rerun. And it's going to do that some number of times. You don't really know how many times, but if you click on this little view convergence data, you will get here, and you will have these two graphs. So here's one. This is showing that it's plotting after it generates a new iteration. It's plotting the value, and this is the stiffness ratio. Let's do the mass target one. So here it's plotting that blue line up there is our target line. I told it I wanted, 346 grams, so that's where it's trying to get. And now it's trying to solve the simulations, making sure that it's converged to a solution. So, it's oscillating back and forth right now. So you kind of see some zigzags in there. Let's check the other one. Oh, I've already got it open, I guess. Here it is. The other one's kind of, sort of looking like it might be approaching some asymptote way down there at, 20-something iterations. So we don't really know how many iterations it's going to do. I think there is a way that we can control how many iterations, but I would rather it just converge, and we'll look at it then. So we'll come back to this in some time. Well, I don't know how long, but it might take a while. Here's where we're at right now. But for now, we'll go look at our printer and see what's going on there. So here's where we're at right now. And it's done, I don't know, looks like maybe 9 iterations. All right. So let's go over here. So I've noticed I've changed out, I have a whole stack of magnetic beds, right? So now that we have our probe on here and it's working, we can just flip another bed on here and everything works fine. This one is one of those ones that has a little carbon fiber pattern on it. I didn't print this one on the on this bed, but I did print a calibration cube just as a predefined object in Cura, and it's not great at all. You can kind of see, can you see? Let's see. I don't know if you can see. There you can, yeah, there you can, I think you can see that there are, I don't know if I can get it to actually focus the right way or not. You can kind of see right in there, there's definitely some missing material. The bottom's all messed up, but that was a adhesion issue. X side looks pretty good. Y is not bad, except this corner is really bad. There's more of those under extruded corners. Z, the top layer is decent. I haven't measured it. It should be 20 by 20 millimeters by 20. So let's see. Okay, what do we have here? Well, so that's okay. Let's see about that one. I can tell that it's gonna do them from there. 20, that's okay. Let's see the height. All right, so the calibration for X, Y, and Z steps seems fine. So that's good. But there's some issues on like the flow rates. So one thing, remember, we have switched over to Clipper. So Clipper, let me see if I've got Clipper running here. I do, it's just I gotta find it. There we go. So we'll go back here. Clipper has, actually, there. I haven't tuned anything, right? And so it does have the ability to do what's called linear advance or pressure advance. I believe, I don't remember which one is which. Let's see. Stepper, extruder. I don't know which one Clipper calls it. I think it calls it linear advance, and other systems call it pressure advance. The idea here on linear advance or pressure advance is that when you get to a corner or a new line or something like that, then if you were able to predict the amount of oozing that's going to happen. So I just printed one layer and I'm going to move up and print a new layer, or I'm going around a corner so I just changed speeds or anything like that. If I'm able to predict the change in speed, that I can stop extruding filament a little bit early and rely on the ooze that's going to happen because there's a lag. Particularly, there's more and more lag the longer the Bowden tube is on your printer. And if I can predict that, then I can get a smoother corner. Well, not like rounding the corner, but I will get a less Z seam and all that kind of thing. Now, what I've got here is definitely not right. So this one, definitely not right. So one thing that's affecting that is that I've never done the PID tune. Remember when we installed our new Clipper, I just took the default values, and those default values are assuming a brass nozzle. I did switch this to a steel nozzle, a hardened steel nozzle. So PID tune in Clipper, I've linked here to the description. PID is basically proportional, integral, and derivative, so that I get a better control over, in this case, a heater. And the command for it is here. So we're just going to copy this guy, go over to our console. Oh, go on the dashboard, go to our console, paste it in. I'm actually going to have the target at, I like to print at 205, so I'm going to make the target 205. Actually, remember, we really want to do the carbon fiber polycarbonate, which is going to print way hotter. So I might redo this later once we're ready to print that material at a higher target temperature. So I'm going to send this, and it has set the target temperature here to 205, and it's heating up the extruder. Okay. Oh, it looks like my main camera froze again. It does like doing that. Last time I tried to fix it, though, it crashed everything. So I'm kind of reluctant to fix that because I don't want it to crash just yet. So, and it's just my picture. You're just frozen. I'm frozen right now. All right, so you can kind of see it's ramping up, and it's going to, I don't know the default number of cycles it's going to take. It looks like, based on this picture, it looks like there's 1, 2, 3, 4, 5, 6 cycles. You can change that if you want to, but we're going to do just the default 6. And while it's doing that, let's check in on our SolidWorks. Oh, it's done. Oh, wow, it gave us some really interesting results, but still, it gave us some results. So let's look at our SolidWorks here. All right, this is what it told us. So I don't know, I've never seen a connecting rod quite that shape before, but that's what it thought was best. We probably should have put some, forces in these bolt holes here, showing that there's clamping force and all that kind of stuff. We left off lots of forces for sure, but you can kind of see here of like based on that one simulation and those minimal set of constraints and the starter geometry that we gave it, it thought this would be a good option. I don't know that that's particularly a great option, but that's what it thought. There are other stresses. We did a perfectly vertical compression load, perfectly axial might be a better way to say that, axial compressive load on this thing, and that's not quite true, but that's what we're going to work with here. So what you would do next is you could do one of two things. You could just take this and say, okay, I'm going to go design this shape, and I know I've got some things. I didn't put a fillet here and none down there. I don't really like the way this is happening. I could probably beef this little divot. I could probably get a little more out of that. You could rerun the simulation with more requests or more constraints, or you could just right click on this thing and export a smooth mesh. So that's what we're going to do, and we will do a new part file. You could do a new configuration. That's what they want you to do, but I'm going to just make a whole new file, and we'll save it. Where are we saving this thing? In our topology study. It's a good enough place. Okay. So it's thinking. All right, so it has exported a smooth version of this. So let's look at that. If we open our folder, that was on the desktop. I had created a folder called 2024 TO, and then we want a smooth version. Not that one. We want 1013. We want that one. So we'll open this with. We'll just open it with Mesh Mixer, just because we don't want to actually do anything. We just want to see it. So here, here's a smooth version. Oh, I thought that little indentation was just a dent, but it's actually a hole all the way through there. That's interesting. Haven't seen a rod like that before. But you could take some inspiration from this thing. So what you would do now is, as the engineer, you would go in and make some decisions like this little indentation here, probably not good, because we didn't really put any of we put the constraint that this surface was held still, but we're probably missing a good number of forces. For one, the clamping force in this bolt hole, that's definitely not the bolt hole I would want to have holding the end cap on the connecting rod. This part in here is interesting design, you know, with the slot in the middle. I don't know if that's great. You definitely want to put some fillets around here. The smooth version kind of put some fillets in there. You would not want the, you know, this surface all uneven and jaggedy like it's shown here. But what it does is it gives you some ideas on geometry that you would then go, and you could just print this, but you know, in an engineering sense, you would go in and redesign based on what the topology optimization study told you, and then you'd have to run simulations on what your you know, your interpreted model, and then iterate on that a couple of times and end up with your final model. So that's kind of the general process for topology optimization. Again, you know, do not do this. I don't think this is a great idea for a connecting rod, but you could do this kind of process. And the more aggressive you are on the weight constraints, the more this part in the middle, in particular in this one, would turn kind of web-like. You know, it would get little strands everywhere and try to not be such a chunky piece, or it would tell you you can't, based on the loads and the constraints that you've given me and the request of how light you want this part to be, I just can't do it. So it could end up that way also. So that's kind of the idea of topology optimization. Let's see where we're at on our, I'm going to close this down. I'm also going to close SolidWorks because it does eat up a lot of resources. So it looks like we ended up with 366 grams. I think I wanted it to be 350 grams, so it didn't quite get to what I wanted, but got close, I suppose. And obviously there's some problems with the design that we would need to address. But that's the process. Now you would still have to set up your initial model better, and you know, probably have some new constraints, all that kind of stuff. So let's close this. Sure, we'll save it. Just why not? Close that. We can look back at our clipper, and you can kind of see there were the 1, 2, 3, 4, 5, 6 cycles it went through. Now it actually has given us our P, I, and D values. In order to save those, I need to go to the save config. So save config, and it will restart. And if we check our machine printer config files, now the original PID values were, let's see, here you can kind of see that it has commented them out. And then if I go down to the bottom, all of this section in the save config, notice those are different. They have a hashtag asterisk hashtag, so these do get read. They're not pure comments. In fact, you're not supposed to edit down in here, although you actually can. But these are all of the file and values that have been saved through this little set. Here is our bed mesh that we did. Here's the algorithm that it's going to use based on those numbers, and now down at the bottom it has added a set of P, I, and D values for the extruder. We could do the same thing, well, similar thing. Calibrate heater equals heater bed, and we could do the same thing to heat or calibrate our bed. That one's not as critical as the nozzle. It will have an effect on the final print, but not quite to the extent that the nozzle does. All right, so now at least our nozzle should be maintaining the correct temperature better than it was before. I didn't notice if it was widely varying or not, but it should be pretty nice now. And let's go to our camera here. Let's look at our enclosures. I'm going to back up So this is what we're using. 3D printer protection enclosure from UPI, Amazon. There are a bunch of these. I'm not necessarily endorsing this particular one. It was probably the cheaper one that I saw that day. So in fact, let me see. These are normally in the $40-ish range, and they can go higher, but that's probably what I saw here. Let's see. It might even show the one. Yeah, here's the one I bought. So it was $37.79. That guy right there. And so inside this box is a bag that your printer can go in. And the frame of it is all of these kind of things. So all little rods. So you have to kind of assemble the frame. Another one. This one, I think maybe the reason I did get this one is it did have a light bar with it. It looks like the light bar is powered off of USB. And since I'm running the Raspberry Pi, I think I can power it. In fact, let's test that right now. I think I can power it off one of the USB ports of the Pi. The power supply I'm using on the Pi is a 2.5 watt power supply, so I think that will be enough for powering this guy. Let's find out. Because it does have a big clear window on the front, but you get, you get it plugged in, and you want to see inside there, then a light would be helpful. So let's see if I can power it. Oh, wow, yeah. All right, so can power it off the USB of the Pi, and it has one of those little switches. I can't really quite get it on the. There we go. It has one of those little switches that can turn it on and off. And then got a lot of little corner brackets and connectors to build the thing. So I don't know if I want to build it on the stream because it's pretty obvious how you build it. But the next time that we're looking at the printer, I'll have it inside this enclosure. Oh, it does have a 180-day warranty also, so good for it. I did also get, it's not here, let me get it. I got this, so exhaust pipe for one of these enclosures. So I do want to print things that are, I don't know, not the things that you want to normally breathe. So if you have a material that you're either it just doesn't smell right to you, or you know that it's a little bit noxious to breathe, they do have these little guys, and all they are, you could make them pretty easily, but all they are is a PC style fan and a duct. So I'll try and get the fan out here so you can kind of see it. Let's see. So PC DC brushless, another 0.4 amps, 5 volts. So that is also another one. Now, how many of these things can I run off of the Raspberry Pi at the same time? I don't know. You know, I've got a 2.5 amp power supply. The LEDs probably don't draw that many amps. This thing says it's going to draw 0.4, so I'm left with 2.1. It's kind of like a budget, you know, where you've got 2.5 amps and every little thing eats up some of it. I am not powering the printer with the Raspberry Pi itself, so I don't have to worry about like trying to supply power to the heaters or anything like that. But I am now powering a LED bar, the screen that's on the Pi, I'm powering that. The Pi itself is getting powered. The I said the LED, and now this fan. So let's plug the fan in and see if I can power both of those at the same time without some kind of brownout situation. Let's see. So I did get this one also because it will just plug into the Pi. The Pi has 4 USB ports on it by default. Oh, all right, so that's on. It's actually a little bit, not terribly loud, but it's actually moving quite a bit of air. Light is on. I didn't notice any issues with the screen or anything like that blinking out on me. So I'm going to turn this off before it chops my fingers. And turn that off. So if you have something where you want to exhaust, so here's the little exhaust. I'm not going to open that up just yet. You do have the options. Most of these enclosures, I'll see if I can, since I don't have the enclosure built, I'll see if I can find a picture of it here. Yeah, so let's see. You can kind of see in the bottom corner there, there's usually a flap or two where you can either open up just that flap to get to the printer for access without having to open the entire door, or you can do an exhaust port, or they usually have several options on how you can connect to them. Now, if I'm trying to maintain heat, then I probably don't also want to exhaust, but what I can do is set it up, maintain the heated chamber environment, do the print, and then before I open it to get the print out, I can exhaust everything outside or wherever I want this exhaust to go. So you don't have to exhaust while you're printing necessarily. You can just exhaust later on, exhaust it through a charcoal filter or whatever setup you might have, so that you're not just sucking all the hot air out of your chamber. And it looks like this one does have just the one exhaust port on there, so maybe I'll have to print maybe a mounting plate that'll fit that panel and match up with our fan. I'm trying to show you on our camera that's frozen. Our fan. So I think we can do something like that probably. I don't want to cut a hole in the thing unless I guess I could. I could do that. I could cut a hole in the back somewhere. We'll build it first and see what happens. All right. Let's see. We've got a little bit of time left. Let me tell you where we're headed next. So I'm going to build all of this. So the printer's in a chamber. I do need to still get the web cam working. So the little Pi cam that's attached to the Raspberry Pi, I need to get that working. Or I do have one USB port left on the Pi. I could plug in a USB webcam if I find one. So I could use one of those as our option for remote viewing of the printer. Get it in its chamber. I now have a PID tune on the nozzle. I'm going to do a PID tune on the bed. It'll just look the same as the nozzle. I also have, just for a little bit more durability, I think I would wait and do this one on a stream, but we're gonna, oh, I need to open it. Hold on. I'm going to change out the feeder, just the mechanism itself, not the stepper motor or anything like that, but I'm going to change out the feeder with this guy. So got a dual-sided drive for the feeder. It's all going to be metal. We actually have this little cable. So if you get one of these, this is a micro Swiss one, don't think that this is unnecessary. What this does is, a lot of times these guys are driving on the opposite side of where your filament currently is being driven, and what that'll do is it'll make extrusion retraction and retraction extrusion. It'll make it backwards. And what this little cable will do is you plug this in between your existing extruder cable and your stepper motor, and it will reverse the direction. So it's a reversing cable is what that little tiny short thing is for. So don't lose that if you go get one of those. I will say, and I'll show you this when we actually install that, but the way that the Ender 3s and maybe other printers currently are being set up, and maybe I can get your camera over there. Let's see. I don't know. There's kind of a lot of stuff up here. So yeah. So this little pulley, this little brass pulley right here, not pulley, but roller. This is a pinch roller setup. So this one right here on the existing setup is just kind of spring loaded and pinching the filament between the idler and the roller here. And we want to change both of those. So in our new one, they're both going to have to be changed. This one just comes off when you take the capstan, the plastic part off. This brass one is heat shrunk onto the shaft of the stepper motor, and you will not get it off by just pulling it off. You will have a hard time getting it off any other way, but what I end up doing is I have this tiny little puller for like RC cars, and it will, so far it has not failed, and it will pull this guy off of here. Let me see if I can find it in Amazon real quick, and I'll show you the one that I use. This is the one, and yeah, it doesn't have great ratings, 3.5 out of 5, but it's only $10, and actually you can get 5%, or at least I can get 5% off today. And I've had this one November 3rd, 2022, so, and it hasn't broken. It's the right size for these things. So if you do want to go that route, and you notice that on your existing setup, this is not held on with set screws. So some of these have little set screws that you can just undo and they slide right off. But lately I've been noticing that most of these come pressed on, and it is hard to get them off. If you don't get this little puller, then you can try heating them. So they are brass compared to the steel shaft, so they can heat at a different rate. So you can try heating them, maybe over a candle or something like that, and then using a combination of like pliers and screwdrivers to pry them off of there. But you might get that to happen, but I've just not had great luck with that. But I have had luck with this guy pulling them off of there. So just check before you go and change out any of where's that? Check before and make sure that this is going to come off without a puller, or you're going to have to find some way to pull those off, or just leave it alone. This is fine the way it is. I just do like I like two things about our new version. Is one, that all the pieces on the old one that are plastic are now metal, so I like that. But the real part I like is that it drives from both sides. So instead of this one being just a passive roller, they're geared together. Let's see if I can see how there's little gear teeth on even on this one. This is the one that's kind of on the lever arm here, and it has gear teeth that match it with the one that's on the stepper, and they both drive together. And so you just get a more consistent feed that way. Probably not that noticeable, but we're going to do it anyway. All right, so we're done a little bit early today. I'm going to go ahead and build the chamber so that we can have that going, and then next time we'll look at putting our new pieces on here. Look at make sure our chamber actually does anything at all. It will at least enclose it, if nothing else. And then just the way that we did SolidWorks in Topology Optimization, I plan to do Fusion with generative design. So it's the other version of this same process where you start out with just your constraints and boundary conditions, and it kind of grows the material between them. So it's more or less the same, but it's slightly different. So we'll do that, or at least I plan to do that in class Wednesday, and some of our printer stuff. All right, we'll go a little bit early today, and see you on Wednesday.